In this video, we're going to go over finding the solution to a differential equation that satisfies a given initial condition. We're also going to be looking for an explicit solution of the differential equation, so we'll want our final answer to be in the form y equals some function of x. All right, let's take a look at this differential equation we're given. Y prime equals e to the x plus y. Now, this single term, y prime, when we're going to go ahead and try to use the separable equations technique, it doesn't look like a dy over dx right now, but it's a first derivative nonetheless, so we can actually rewrite this left-hand side first to take the more familiar form as a dy over dx. And the right-hand side, still the same thing. So again, just turning that y prime derivative into the other derivative notation, dy dx. And the reason we want to do that is so we can do some algebra to collect all the x's on one side of the equation, all the y's onto the other side of the equation. So let's go ahead and move through some of those steps now. The first thing we can do is, well, take the dx and multiply it to the right-hand side. So multiplying both sides of the equation by dx, we get dy is equal to e to the x plus y times dx. Now looking at this right-hand side, we still have some y dependence over there, so the equation isn't separated completely. All the y's on the left, all the x's on the right. So we have to do a little bit more algebra to help get all the y's on the left, all the x's on the right. So let's think about how we can do that for a moment. And the answer comes to us through using properties of exponential functions and properties of powers in that way. So we can basically take this e to the x plus y, and we can write this as a e to the x times e to the y equivalently. So now that we've done that, we see that, well, we have that e to the y term that we're just going to be able to divide both sides by to get all the y stuff onto the left side. So let's go ahead and divide both sides of the equation by e to the y. So we have dy over e to the y is equal to e to the x dx now. So now we have all of the x's on the right, all of the y's on the left. So we've separated the equations. The next thing we can do is integrate both sides. We're going to integrate the left-hand side with respect to y, because we have the dy there. On the right-hand side, we can integrate with respect to x because of that dx there. So let's just rewrite this left-hand side to put in a little more familiar form. Since we have a 1 over e to the y, we can equivalently write that as a e to the minus y dy. On the right-hand side, I'm just going to keep that as the integral of e to the x for right now. But the thing to notice is both of these integrals, the left side as well as the right side, we can compute in a pretty straightforward fashion. So the integral on the left-hand side becomes e to the minus y all over minus 1. On the right-hand side, when we integrate just e to the x, that's an e to the x. And now because we did two indefinite integrals, one on the left, one on the right, well, we only need one integration constant, so we'll just put a plus c on the right-hand side to satisfy that. So this equation that we're looking at right now looks like e to the minus y when I multiply both sides by minus 1. So I should say multiply both sides by minus 1. This looks like a minus on the right-hand side times e to the x plus c. And the reason why I want to go through this step is we're going to distribute that minus 1 into both terms in a moment. So again, we're going to take that minus 1, distribute it into both terms in parentheses. But we're going to take a note at one specific thing happening. We get a minus e to the x, and we get a minus 1 times an integration constant we don't know. Since a minus 1 times some number that we haven't yet defined, well, that's just going to be some other number now. We can actually just keep that as a plus c. Since we haven't defined that c yet, so if we multiply it by a minus 1, that's still going to be some number that we have yet to define. So we can just keep that as a plus c. So we can rewrite this as a e to the y equals c minus e to the x. And at this junction, we have basically an implicit solution to our differential equation. because we have some function of y on the left equaling some function of x on the right. Now, we haven't yet used the initial condition yet, so we can go ahead and use that next, or we could solve for the explicit solution. What I want us to do is, at this point, use the initial condition. And the initial condition that we're given in this problem is basically that y of 0 equals 1. So let's think about this for a moment. What this actually reads to us is, basically it says when x equals 0, y equals 1. So again, we have x equals 0 and y equaling 1. So we can substitute both of those information into our solution that we have up above. So we have e to the minus. Now substitute in that value of y. We have 1. So again, this is saying y equals 1 equals c minus e to the 0, because we have x equaling 0 in our initial condition. All right, so the only unknown we have left in this equation is that value of c. So we can go ahead and try to solve for that next. Now on the left-hand side, we have that as e to the minus 1. So this thing is really just a 1 over e. On the right-hand side, this is a c minus 1. So altogether, the way in which we can write this and solve for c is just add 1 to both sides, and we find that c is equal to 1 plus a 1 over e. So that's our integration constant to substitute back into our solution up above. So what our solution looks like, so I'll just say substitute integration constant. So again, we're just going to take the solution we had prior and just put in what we know c to be now. So we have e to the minus y equals c, which is 1 plus 1 over e minus e to the x. So the last thing we're told to do in this problem is look for an explicit solution of this differential equation. So right now, we have an implicit solution in which we've used the initial condition. So we have a functional relationship between y and x. But an explicit solution would be when we have just a solution that is y as a function of x. So we're going to solve this equation for y as a function of x. And the way in which we can do that is looking on that left-hand side, we have an exponential. So what we can do is, well, we can take the natural log of both sides to help us get what's in that exponent of the exponential by itself. So let's do this in 2 steps. We'll take the ln of both sides, or the natural log of both sides, now on the left-hand side, what we have is just the ln of an exponential. So we're just going to get back what's upstairs in that exponential. So left-hand side is going to reduce to us as a minus y. The right-hand side, well, that it just is going to be what it is. Ln of 1 plus 1 over e minus e to the x. And the last step for us is just to get y by itself, which means multiply both sides by a minus 1. So we get y is equal to minus the ln of 1 plus 1 over e minus e to the x. And that is our final solution in this case.